ensure the next level at all. But in complex analysis, the fact that it's differentiable once ensures all the ensuing analyses. So if it's differentiable once, means immediately that you can differentiate infinite number of times, and actually means that it's analytic also. Okay? So this is why it was important. But this, because find xi, the potential function, stream function, this is Cauchy-Riemann equations, they suggest that we define this function, which we call the complex potential, and now we got for free that it's differentiable, the complex potential. Okay? And for two-dimensional flow, because n plus square phi is 0, n plus square psi is 0, this means that also n plus squared f is 0. Right? Okay? Any question about that? That's okay, but again, why we're stressing that this is brilliant assumption, we got some advantages, but what makes it that so useful? What is the main characteristic of, what's the main property of this equation, or the n plus squared phi, or n plus squared psi? What's the main characteristic of this? When you look at it, what do you immediately get? If you look at it and what makes it happy? What makes you happy immediately when you look at this equation?
It's linear.
It's linear. So what? Its solution is easier? That's right. But more than that, linear equation admits superposition. What do you mean by superposition? It means that I can break down my complicated problem into very small problems, and I solve each one separately. It's a small problem, its solution will be extremely easy. I get a solution, then I add all these solutions. And you can see it right away. For example, let's look at this flow field. So this involves the idea of elementary flows. Elementary flows. The first one, uniform flow. Look at this, you cannot get simpler than that. Just wind, there is no body. U infinity, x and y, alpha. There is no body. It's just wind. So you already know the velocity components. U is u infinity cosine alpha. V is u infinity sine alpha. I already know the velocity components. From the velocity components, I can go and construct phi and psi, add them together to get f. Right? So I have f of my uniform flow. It's u infinity e to the negative I alpha times z. Z is the complex alpha. Okay? Actually, I didn't solve anything. It's already known. And I can construct another very simple flow field, the source. So here we have x and y, add the origin out to the source. So flow field that is completely radial with mass flow rate, specific mass flow rate, meter square per second if 2D, meter cube per second if it's 3D. And you have the flow is completely radial. VR is, it goes 1 over r. It's very fast near the source and decays away from the source. So Q over 2 pi r, it's 1 over r, and there is no tangential velocity. Okay? So, again, go and construct your complex potential. This is u infinity, I'm sorry, there's no u infinity. It's Q over 2 pi ln z. Any of these flow fields, this flow field has to satisfy both, right? Continuity, apply dot u equals 0, and irrotationality, apply cross u equals 0. So they naturally satisfy these two equations, and you can construct your phi, the fact that you can construct phi and psi already ensure that they satisfy these two equations, right? Because psi, if you construct psi, it means that it naturally satisfies continuity. If you construct phi, it means that it naturally satisfies the curl equals 0, right? So you construct both, means that you got to satisfy both, add the two functions together to get your f. This is what you had in your 136 or 230A or whatever. Then we have a vortex, for example, right? It's the other way around. Now we have a flow that rotates. We already considered this last time. So this is actually R and theta. So again, we don't have any radial velocity, and the flow is completely tangential and goes 1 over R. So you can construct your complex potential. It's Q over 2 pi I ln Z. So as you can see, these are very, very simple flows to the extent that I don't even need to solve the differential equation. They are really simple. But then I can mix and match these solutions. I can simply add the velocity components to get the velocity component around a more complex thing. Like what? Let's see. So, for example, let's mix and match. So this is the effect of the superposition. If you have a source and source, this is x and y. I have source here. This distance is a. Another source in the same distance. Q and Q. What'd you get? What'd you get? Let's see. So this guy goes like this guy goes like that. See that this is a stagnation point, right? And actually, yes, so this guy's like that, this guy's like that, this guy's like that, this guy's like that. This is actually the flow on a wall. This is a wall, okay? So you will find that psi is constant along x equals 0. So source plus source gives you a wall. You have the complete flow field. Just add velocity components. Add phi's, add psi's, add whatever. Add everything you like. Let's have a uniform flow plus a source. Let's look at that. So this is x and y, uniform flow, u infinity, and I have a source here. What do you expect to form? So this guy is moving like this, and this guy is moving like that. I must have a stagnation point somewhere here, right? When the flow from the source is strong enough. And around the stagnation point, I have this kind of thing. Right? So this is actually half Rankine body, the flow around this body. Okay. So I know completely the flow field. Why? Because I know for uniform flow and source, I'll simply add them together. And if you put a sink here, what do you expect to get? If you put a sink here, what do you expect to get? So these two things will come and close because the sink will just sink them. Okay? So if you do uniform flow plus source plus sink, you will get the Rankine body. So this sink will sink the flow in this region. Okay? And you can keep doing that to construct the flow around more interesting shapes. Then you can actually start to construct more elementary flows like the doublet. So the doublet is an elementary flow actually, it's not a body. So we have here X, and we have sink here, negative Q, this distance is maybe A, and this is another A. I have a source there, Q, okay? And the doublet is source and sink in the limit as Q goes to infinity and A goes to 0, 2A goes to 0. I shift these guys close to each other and increase the source and sink, the string. So what do you get? Well, we get something like that, right? The source will emit flow, and the sink here will just sink this flow. So we get something like this. Okay? So this is a doublet, and we can add the complex potential of each guy and take the limit as Q goes to infinity, 2A goes to 0. We define the strength of the doublet to be 2QA. So we're multiplying a very large number by a very small number to get a finite number. And actually the complex potential for it, you can show that it's K over 2 pi Z. So this is a new elementary flow, which is actually essential in the following step. If you do uniform flow plus doublets, so we have the following. We have the doublet, and we have uniform flow, U infinity. What do we get? So this guy is going like this, and by the virtue of the flow field here, it will go like that. Exactly. This is the start of it. This is the cylinder. Flow around the circular cylinder. So this is equal to cylinder. Now we're getting to more interesting shapes. Okay? This is the flow around the two circular cylinder, and I will do this in a bit of detail just to do some training, and because we need this example anyway. Any questions so far? Any questions? So you can see it's just this assumption that the flow is irrotational that opened everything. We arrived at this linear equation meaning superposition. We started to constructing very simple flows for which I didn't even need to solve the differential equation. I know the solution already because it's too simple. Then just keep adding stuff together. Now I arrived at, I know completely the flow field around the circular cylinder. Okay? So let's get it. So F, the complex potential, for uniform flow, it's U infinity, e to the negative I alpha, there is no alpha, times Z, so it's U infinity times Z. Plus, for the doublet, we just wrote it above here, it's K for the doublet over 2 pi Z. This is your complex potential, okay? I don't think that we stated how to get the velocity from complex potential. Here, when we introduce the complex potential, Let me do the following. Let me just give you this piece of information. I'm sure that you know it, but just to have to be self-contained in this lecture, in this course. Remember, when you have any function, any complex function like this guy, and you want to differentiate it, f prime or df by dz, how you differentiate it? You know, if it's a function of z, you will differentiate it just easily. If it's maybe z squared, it becomes 2z, that's fine. But if you have the components as function of x and y, how you do it? How to differentiate with respect to x and y, whereas the derivative here should be with respect to z. So there's a formula for that. It's simple. It's actually the average of the differentiation. So it's half phi x plus psi y. This is the real part of it, plus I, the other way around, psi x, and again this is half here, psi x plus psi x negative, sorry, psi x negative phi y. Okay? So let's apply this. So we have half phi x is u, psi y is also u, correct? Plus I over 2, psi x is negative v, and negative phi y is also v. So you can see that this is simply u minus I v, which we call the complex conjugate of the velocity field. Okay? So finally, what's the conclusion? If I have f, the complex potential, as a function of z, just differentiated with respect to z, the real part is u, the imaginary part is negative v. That's it. Okay? You get the complex conjugate of the velocity field. And in terms of radial component, it's e to the negative I theta. If you want to extract the Vr and V theta, you don't need to do it in a very complicated way. Just take e to the negative I theta as a common factor. Then the real part will be the radial, and the imaginary part will be negative V theta. Okay? So this is how, if you want to get the velocity components from the complex potential, differentiate with respect to z, and either the real and imaginary immediately, or take this guy as a common factor to get the radial and tangential. Okay? Don't spend too much time on it. Any question? This is complex analysis. You need to prove it. So here for our example, I have this guy. This is, I simply did really nothing. This is the complex potential of uniform flow, and this is the complex potential of doublet. I simply added it here. Did nothing. Now if I want the flow field, here it is. It's f prime or df by dz. So this is u infinity